So unlike the case of finally repeated games, for infinitely repeated games, Fock theorem holds even if the stage game only has one Nash equilibrium, like the prisoner dilemma. Again, for example. So just 1 second, infinite repeated games, you could understand it as a game that lasts forever, like to infinity, right? But actually that's not really realistic, right? Because okay, life ends at some point, even the universe has age, right? Just what I said in the textbook. I will have like a stylized example later, but contradicting to that. But anyhow, you should understand it as a game in which all the players, none of the players know when it ends. So the ending point of the game is indeterminate. So at this current period, they play it, no, but they're not sure if it lasts for the next period or how many more periods it lasts. So it has some uncertainty in there. And that's exactly the point when we could apply it only for a case with one Nash equilibrium. However, there's one problem. So before we could sum the payoff up across all periods, right? And then we take the period, the average. And then we compare, we analyze that. Okay. However, now with infinite number of periods, like indeterminate or infinity, you can't add up the payoff for all the periods, because then it will be the product or the result will be infinitive. And how to compare infinitive with infinitive? No, algebraically. So therefore, we apply a discount factor denoted as delta. No, this is what we said briefly before and why it matters with this discount factor. In order to discount all the future flows of payoff back to the present value. It may sound familiar to some of you who has a little bit learning with, for example, project evaluation or finance. Yeah, it's similar to the concept of the time value of money. Yeah? So you discount the future payoff or future cash flow back to present value, and by that you could compare it. And by definition, a discount factor should lie between 0 and 1, right? Not larger than 1, because what you receive in the future will be less favorable than what you receive today. So when you discount your future payoff back to the present, the absolute size of the payoff will get less. What actually makes the Fock theorem work for infinitely repeated games, even in the case of only one Nash equilibrium for the stage game, is the trigger strategy. Now, so the trigger strategies, like I said, is a threat that players used to scare the other players away from deviation from cooperation. Now, for example, I said, okay, if you think on me, I will be very harsh to you in every stage game in the future. That's a threat, right? That's a trigger strategy. And for the trigger strategy to work, to keep the cooperation among players, then must be severe enough. And the key point here is because the ending point of this repeated game is indeterminate. No? So none of the players really know how many more periods is ahead, right? So they may be worried that, okay, if there's many periods ahead, then such a trigger strategy will make them lose more than what they have earned by deviating, right? And thus keep the cooperation. Okay, so now let's do quickly the infinitely repeated games for the personal dilemma and see how the discount factor works or what role it plays in this case, right? But before that, remember one thing. So the discount factor delta is a positive number but smaller than 1, right? So that everything in the future when you discount back to the present time will get smaller. That's the idea, okay? So here is the normal form of the stage game that I put again. Now let's say the scenario where both players stay silent, so they cooperate now every period until infinity, indeterminate. Then the payoff will be VED, denoted for like payoff when they cooperate. Don't ask me why ED, I don't know. It's in the textbook, so we make it consistent. So for this current period, no need to discount, so the payoff will be 2, right? Because it stays silent. Plus, okay, for the next period, I need to discount back 1 period, so 2 times delta. And then for the second period further, I need to discount back another time, so 2 times delta and times delta again. So delta square. And then for the next period, I have delta to the power 3 plus. So every period in the future, you put another delta in. And so and so and so and so until infinity. And we could factor out the 2. Now, inside we have 1 from the first one plus delta here plus delta square plus delta to the power 3 and so and so and so until infinity. Now, so now one important thing to know here is this one. S is called infinite power series, which is equals 1 over 1 minus delta. Just know that, no need to prove it now. I mean, if you want, you can come to me, but for now, just don't make our life more complicated. I would not prove it here. Okay, so that's, we could rewrite already 2 over 1 minus delta. Now, then, okay, That is when they cooperate. Now, if one player deviate, we would have this following pair, present value of pair actually. So here we could have deviate, denoted DEV, which make more sense now. So now if he deviate, that will be free for the period that he deviate, because here, for example, the other stay silent, he will be deviate, so he get free. And then every period after, the other guy will take revenge, right? To punish him, always think, and the best thing he could do is also to think, because what else to do, right? It would be stupid if he stays silent then just to punish himself because he got the payoff of 0. So they will go back to the original Nash equilibrium, and that would be the next period is 1, right? The payoff times the discount factor because it's already the next period, plus the next period also delta square with 1 also here, but right now we can just forget it, and 3 and so and so and so until infinity. So at the end you would get 3 plus delta factor L1 delta here, so that in the end we have something that we could use this. So here inside we still have 1 plus delta square plus so until infinitive now. And make use of this fact, we would have 3 plus delta over 1 minus delta, right? Again, this is actually the same thing over here. Now, let's say in order to keep the cooperation, how can the cooperation be sustained? That is, what you earn from cooperating must be more attractive than what you get from deviating, right? So that means VED must be larger than VDEV. Substitute them in 2, so 2 divided by 1 minus delta must be larger than 3 plus delta divided by 1 minus delta. And because 1 minus delta is a positive number, right? Because delta is smaller than 1, we could multiply both sides by 1 minus delta without changing or flipping the sign here. So that means 2 larger than 3, 1 minus delta plus delta, and you can distribute to open the bracket 2 larger than 3 minus 3 delta plus delta, and that means 2 larger than 3 minus 2 delta. And now we could also rearrange it in a way that, okay, you have 2 delta larger than 1. At the end you have delta larger than 1/2. And this is what written on your slide. Actually, this is a strictly case, but on the slide, it's not the strictly, so it's weakly, so larger or equal is here. Just avoid confusing you. So it could be also equal, but in my opinion, larger is a stronger incentive to cooperate. So in order to keep the players cooperate, the discount factor must be larger than 0.5, so that the present value of what they earn from cooperating is larger or more attractive than the value they get from deviating. Now the trigger strategy that we've seen in the derivation on the board, and also what I said before, in which players revert to the very harshest punishment possible when the other player deviates, is called the cream strategy. So it involves player reverting to the stage game Nash equilibrium forever. That's it. Never forgive. So because this potentially implies a very severe consequence in a long future, it would facilitate the cooperation even for the lowest value of the delta for any strategy. It works. So delta or the discount factor doesn't have to be very large in order for the cream strategy to work. However, there's also less severe strategy. It's called tit for tat. That is, the punishment only played once. Every deviation will be matched by one punishment later. So an eye for an eye. And because this is less severe than punishment forever. So in this case, you will need a significantly larger discount factor. And as the discount factor approaches 1, the cream strategy punishment becomes very harsh, like very harsh, because it will not potentially, but for sure, give you infinitely negative stream, a loss stream. So cream strategy is already severe, even with low value of discount factor. But cream strategy with large delta is the worst. So in general, the fourth theorem for this case, infinitely repeated game, says that feasible payoff, which is higher than the pure strategy min-max value obtained by some sort of cooperation in some subgame perfect equilibrium. So these corporations now consider subgame perfect equilibrium of the infinitely repeated games when the discount factor is large enough or closer enough to 1. Okay, but note that here, remember what we have seen is we actually already normalized the payoff by multiplied by 1 over 1 minus delta, the infinite sum of the power, the series. To sum up, the fourth theorem for infinitely repeated games is different from the one for finally repeated games in 2 main points. Keep that in mind now. So the limit or the restriction that keep the cooperation depends on the increases in delta, the discount factor, rather than the number of periods, which is now irrelevant because it's indeterminate. The second thing is we have seen that if even when there's only one Nash equilibrium in the state game, it holds. The fourth theorem holds, or cooperation holds, with the restriction that we have set.